Welcome to Organic 2. We're going to start, of course, by going back to Organic 1. And we're just remembering a couple of things from Organic 1 that we're going to pull forward into Organic 2. And what we're going to find out is that it's just kind of more of the same thing. So if you loved Organic 1, I have great news. We're going to do more of that kind of thing today. If you hated Organic 1, I have great news. You get another chance to learn to love it. Everybody wins. All right. So we're going to review three reactions for organic 1. You're going to recognize them because they're going to be the SN1 reaction, the SN2 reaction, and the E2 reaction. So you remember all of those from organic 1. We have some substitutions, we have some eliminations, we've got some carbocations, all that good stuff. So let's start there. All right. So the first reaction that we have here, we have an alcohol, we have an acid, we have a poor nucleophile. This is going to be an SN1 reaction. And we all recall that the first thing that happens, right, is we add our base, our oxygen base to the H plus, and that generates a good leaving group, and then we make the carbocations. OH2 plus, and then this leaves, and we get a carbocation. Okay. Carbocation is attacked by the nucleophile, and we lose an H plus in there to get to our final product. Now, what's important to notice here, right? This is an SN1 reaction. You guys at least have a passing familiarity with that, right? Important things here. Leaving group is activated by H plus, right? We can't have the leaving group leave until it reacts with H plus, right? That leaving group bond doesn't break. And we're making a carbocation. Makes a carbocation. Okay? So those are the things we're going to remember from the SN1 reaction. The next one down, we have a leaving group. We have a good leaving group in this case. We have a good nucleophile in this case. This is an SN2 reaction. We can tell that the substitution is happening, all that good stuff, right? So we reach way back in our minds and we think about, okay, SN2 reaction means that our nucleophile just comes in and attacks. We don't have to do any activation, but the nucleophile attacks and the leaving group leaves all in a single step, right? And then we have to lose H plus in here as well. So I'm going to kind of hand wave away the H pluses as they happen here. But the important thing to notice here is that the nucleophile adds and the leaving group leaves at the same time, and leaving group leaves simultaneously. Okay. So in an SN2 reaction, when we have a good nucleophile, remember this is what defines an SN2 reaction is a good nucleophile, then we have everything happening at once. Nucleophile adds, leaving group bond breaks. SN1 reaction, we have a poor nucleophile, and so then we need to do this kind of activation, make the cation, and then have this thing happen. The last reaction that we have was clearly an elimination reaction, so this is an E2 elimination. We have a good base, right? We have that alkoxide base here, and so we remember what that's going to do is it's going to come take that hydrogen from the neighboring positions. We remove this hydrogen, that makes a pi bond, and this thing kicks out. We lose the leaving group again, right? So remove, E2 is good base, remove the hydrogen from the neighboring position to the leaving group. Okay, so we have basically three ways of getting rid of the leaving group. We can get rid of the leaving group by making a carbocation. We can get rid of the leaving group by adding a good nucleophile, right? And kicking it out that way, or we can get rid of the leaving group by adding a good base and removing the neighboring hydrogen. Now, you've all stopped the video, you've got scrambled back to your Organic 1 notebooks to figure out, oh, which one of these things is what and what's important about these reactions. And that's great, but we're going to move forward on this, right? I'm not going to start asking you SN1 questions and SN2 type questions. What I want you to do is just remember, oh yeah, good base, good nucleophile. These are things that are important. And knowing how to do that is good. And so reviewing that might be worthwhile. But the point is the next slide where we're going to actually get into what are the reactions that are similar to these, that use the same ideas, but we're going to apply it to a slightly different concept. All right, and that concept is carbonyls, right? So these are basically the same substrates, but we've replaced the leaving group in each case with a carbon-oxygen double bond. So if we replace the leaving group with carbon oxygen double bond, do we get, like, what we're gonna see is we get a very similar type of reaction, right? So in this case, we have H plus, we have methanol, so we have a poor nucleophile, just like we did in the SN1 reaction on the previous slide. And so the first thing we're gonna do is this oxygen is gonna go get that H plus, and that's gonna give us this thing. And then what's going to happen is we're going to break this CO bond and make a carbocation here. Now this is just resonance. This isn't a new compound or anything because we're only moving pi electrons around. But it looks like a carbocation. And then of course methanol can come in, add to that position, we lose an H plus and we get to our final product. So notice what's happening here is where the CO pi bond is activated by acid, right? It's broken after adding acid. And we make a carbocation. Carbocation. There we go. So those 2 points should look very familiar because, of course, on the previous slide, we did the same thing. Only instead of having a CO pi bond, we had a leaving group. We had the OH group as our leaving group. All right. So we can see that if we go back, right? Leaving group activated by H plus, we make a carbocation. CO pi bond activated by H plus, and then we make a carbocation. So the same things are happening. So now we have a good nucleophile. What's going to happen here? Our good nucleophile, right, is going to add to our carbonyl. It's going to add to the carbon of the carbonyl because we're going to break that CO pi bond. And we're going to push those electrons toward the oxygen. So we're breaking the CO pi bond, broken simultaneously with the addition of the nucleophile. Okay. So the nucleophile adds in, the CO pi bond breaks at the same time. This is, of course, very similar to an SN2 reaction, only instead of breaking a carbon-bromine bond and losing a leaving group, we're breaking the CO pi bond and pushing those electrons just to the oxygen instead of the bromine. Right? Okay, so you see where this is going. So now what if we have a good base? Well, when we had a good base on the previous slide, we removed a hydrogen from the neighboring position to the leaving group. We're replacing the leaving group with a CO pi bond, and so we're going to do very much the same thing. This O minus is going to come get that hydrogen from the neighboring position. We're going to make a pi bond next to here, and that's going to break the CO pi bond and push those electrons to the oxygen. So we end up with a negatively charged oxygen over here. So when we have a good base, we're going to remove hydrogen from position that neighbors the CO pi bond. And that's how we're going to break that CO pi bond. Do you see it? All 3 of those reactions are exactly the same. What we've done is we've taken the SN2 reaction, we've taken the SN1 reaction, and we've taken the E2 reaction, and we've just mapped them onto a different functional group. Instead of a leaving group, now we're looking at carbon-oxygen pi bonds. Okay? And so for the first half of the semester, we're going to do this for 8 or 9 weeks. We're just going to talk about the types of reactions that carbonyls do. And the good news is it boils down to really the same reactions that we talked about in Organic 1, only now we're doing it on pi bonds. Okay. So And then just to drive this point, I think the next slide I have all three of these just labeled next to each other, right? So we have poor nucleophile, right? This is carbocation and acid activation. This is carbocation and acid activation. This is the nucleophile adds, and the leaving group leaves at the same time. Nucleophile adds, and the CO pi bond is broken at the same time. And of course, the last one, we remove the neighboring hydrogen. And we remove the neighboring hydrogen. Right? So those are the three organic 1 reactions that we're going to use most often as we do this, but they're not new reactions, they're reactions that we have seen before. All right, we have 3 strategies for breaking a CO pi bond. I think I've listed them twice now, so let's list them one more time, right? The first one, we can add acid, right? When we add acid, the acid reacts with the oxygen, right? The second thing we can do is we can add a nucleophile. The nucleophiles will always react with the carbon of the carbonyl. And the third thing we can do is we can add a base. And the bases will react with the neighboring hydrogen. So anytime we have a carbonyl, we always see the same reactivity, right? We have a carbon, we have an oxygen, and we have this kind of neighboring position here. So this carbon is electrophilic, right? The nucleophiles will add to that. So this carbon has a delta plus on it, right? The oxygen has a delta minus. That's the most basic position. So if we add acid to it, that's where the H plus will get added to. And then this neighboring position to the carbonyl here, right? These have the most acidic hydrogens, acidic hydrogen. And so a base will react with this position. Right? So any carbonyl that we see, we're always going to kind of see the same reactivity. It's going to have 3 possibilities it can do. If we're under acidic conditions, it will react one way. Basic conditions, it will react another way. If we add a good nucleophile, it will react the third way. And I think that's it. So I'm going to stop this video here, and we'll jump into some actual examples of those reactions in the next few videos. Enjoy.